Hi everyone. Today's video is going to be very short. What I want to talk about is just 7.3. 7.3 is called Integration Theorems. So as the name suggests, it talk about several different theorems that's relating to Riemann integral. And we're actually going to talk about just 3 of them. So it should be relatively short. There's no homework assignment for 7.3, so it should be pretty easy. Just make sure you write down the theorem correctly and make sure you understand what they mean. So here's our first theorem, theorem 7.3.1, which states the following. Let's say given two function, let's say f and g, let's say they both are the same type of function, so f map from Rn to R, and g also map from Rn to R. So these two functions have the same domain and same range. Let's say that these two functions are integratable over a region B in Rn. So here's an interesting word that I want to point out. So what does it mean by integratable? So integratable basically refer to a function has, when you integrate a function over the regions B, the integral exists. So therefore integratable basically meaning that in this case, integral over B, f of vector x dA, dV in this case, and both an integral over B, g of vector x dV, both exist. So if that's the case, if I know these two functions and I can actually integrate them over the regions B, then what happens is the following. Let's say we'll let A and B be two scalar, two constants. Then this is what is true. Then if I take the integral over B of an expression A, f of vector x, plus b g of vector x dv. So basically what this tells me is that if I integrate over a sum of two functions or a constant multiple function, I can actually just say, well, this is basically the same thing as I can separate these two integral. I can separate these two integral and pull out the constant. So therefore, this theorem basically takes care of two things. Number one is that when you add two functions together and integrate over regions B, you can actually separate into two separate integral and then add them. Or if you have a constant multiple of a function and then you integrate over regions B, you can actually pull out the constant from the integration. Now notice that neither of these two things are new. You have already learned about them in BC calculus, which work out the exact same way with a single integration. And this theorem just basically say that it's also true when you have a Riemann integral in high dimension. This probably actually has a name, usually referred to as linearity, basically meaning that this operation or integration or Riemann integral is what we call a linear operation. Okay, linearity. So basically meaning that this integration or Riemann integral is what we call linear operation. So that's theorem 7.3.1. So I'll show you the next one. The next one is theorem 7.3.2. Which states the following. Let's say given a function f And once again, we say function f map from Rn to R. And let's say f, given function f, and it is integratable over regions B. And if this is true, if the function f of vector x always give out a number that's either 0 or positive, then what we know is that the integral over b of f of vector x dv will also always give out a number bigger than 0, bigger than or equal to 0. So in here, what you have to do is understand the following. So what this statement basically states is the following. Remember, in this scenario right here, okay, okay. In this scenario right here, important to realize the following. In this case, the function f of vector x kind of represent the height, okay? And then b kind of represent the base. And so when you form this integral in a way kind of represent the base area multiplied by height, which is representing volume. So in this case, this technically speaking, it actually represents what we call net signed volume. But if f of vector x is greater than 0, that means we always have a positive height. Because remember, the function f of vector x represent height. So we have always a positive height, then what we actually form will always be a positive volume, because the base area have to be positive. So here's the tricky part that you have to understand is that no matter what b represent, in this integration, the b represents the regions, the base, and when you try to calculate this integration, you're basically multiplying the base area by the function f, which represents height. So the base area will have to be a positive number because no matter where you draw b in Rn, it will always have some kind of positive volume or positive area. And if you think about it, just in R3, for instance, if you just look at the xy plane and draw some kind of region xy plane and calculate the area, that area have to be positive. So if the height is positive and the base area is always positive, then the output will always be positive, which in this case, what does it imply is the following. It implies that this function, of course, is always positive because that's what the theorems say. But more importantly is that this integral, this Riemann integral, now actually represent strict volume. Not net sign volume anymore because it can be negative. So therefore, I can just simply call it volume. And of course here, please understand that this volume should more properly be referred to as n-dimensional volume, okay? Because not always has to be in R3. So important to understand is that the distinction between net sign volume versus just volume. And in here, if you think about it, you actually have a similar theorem that you learned in BC calculus, which says something like if a function f of x is always greater than or equal to 0, then the integral of f of x is always greater than or equal to 0 also. Which basically is saying that if f of x is always positive, then the integral of f of x will always give area. But if f of x can be positive or negative, then integral of f of x would give a net sign area where you could have positive area cancel a negative area. This theorem also has a name. Positivity. Basically meaning that if the function is positive, then the integral is positive. All right, and now move on to our last theorem. So the last theorem is theorem 7.3.6. Yes, we're skipping all the one in between. Because some of the one in between are just leading up to some of these other theorems. So what is this theorem state? Well, this theorem states the following, and which is something that also they are pretty much equivalent to it that you learn in basic calculus. So this theorem states the following: if function f is integratable, and of course here function f is a function map from Rn to R, just like what we talked about before, over two disjoint regions. Let's say, so we're going to have to talk about what disjoint means. Okay. Disjoint region. Let's say they are B1, B sub 1, and B sub 2. Then this is what must be true. Then if you take the integral over the union of B1 and B2 together, that would have to equal to the integral over B1 plus the integral over B2. And if you think about it from a geometrical standpoint, it makes sense in the sense that when you integrate this, that you get the volume over B1, and then you integrate this, you have the volume over B2. So when you add them together, you get the total volume over B1 and B2 together, which is what this state. Now, but of course, there's this one important word that needs to be considered, and that's what the word disjoint. So what does the word disjoint mean? So two disjoint regions basically means the following. Basically means that these two regions do not overlap each other. Or from a more mathematical term, that means that the intersection between these two regions is 0. It doesn't have an intersection. Now, as a matter of fact, the interesting thing about this theorem is that we actually not going to use the theorem the way it's presented, so to speak, but kind of backward in a way. So show how this theorem is being used, and that will probably be the last thing I'm going to talk to you about for today's video. So the proper way to actually use this theorem is actually the following. So let's say given the regions B, and let's say we could subdivide regions B into a list of disjoint regions. So let's say B can be divided into n disjoint regions. And let's say this disjoint region would be B sub 1, B sub 2, to B sub n. Then what I can do is the following, is that I can actually claim that if I take the integral over B of some function f of vector x dv, I can then say, well, that, technically speaking, is the integral of B sub 1 union B sub 2 union union B sub n of f of vector x dv. And in this theorem, I can therefore say, well, I can then now separate this into a whole bunch of integral. And what this will allow us to do is allow us to actually divide complicated regions into smaller, simpler regions, and then integrate them individually and hopefully come over the answer. Now, once again, none of these three theorems should be surprising to any of you because it's actually very consistent with what you know about integration from basic calculus. And as a matter of fact, that's the beauty of it, is that even though we increase the dimension of our integral from a single integral from basic calculus to now what we call Riemann integral, multiple integral, where we're trying to integrate more than once within the integration, some of these properties that we learned already and we expect already are still in play. So therefore make it easier for us to do problems. All right, well, that's it for today. Okay, hopefully I'll talk to you guys soon. And remember, this is our last video for this week. And next week we'll start our first video on 7.4. And also don't forget to work on your take-home test. Okay, see you guys soon.